talk to you guys about Hadoop with Python, and let's see. So this talk is so it's a real talk, but I'll give you my ulterior motive here. So I have a tutorial at PyCon in Montreal, and so this is a distilled down version. I decided I'm not going to do the whole 3.5 hours for you guys, but so I guess one thing that I want to kind of point out before I start to talk is if you have any suggestions or thoughts or anything like that, please let me know afterwards so that I can make it better for the tutorial. In general, this is a topic that's really interesting to me because can everybody hear me okay? Okay. This is a topic that's really interesting to me because a little bit of background on myself. In grad school, I did pretty much everything in Python for my grad work. Did a bunch of machine learning stuff, a bunch of AI, and it's kind of where I really picked up Python, and I really enjoyed it. And then my first job out of college was working with Hadoop, which was all Java, and I still don't like Java. And so with Hadoop, I'll be giving an introduction about Hadoop and what it is, and talk to you guys about why it exists and why it's cool. But I really like Hadoop, but the one thing I don't like about it is Java. And so I feel like if I spread the good news and say like, hey, there's some like inklings of community around Python and Hadoop and stuff, and I'm talking to you guys, and even if just like one of you guys went out and was like, I'm going to help this thing happen. That's I've done my work, right? So this talk will be very honest. So there's a lot of, I'm not going to try to sell you too hard on doing it because I'm not going to lie, I still do a lot of stuff with Java when I need to. So I want to be honest with you guys about what works and what doesn't, and have an open conversation too. If you want to know why something doesn't work or something, or you have a question, just interrupt me. I want to hear what you guys think. Okay. All right. So, unlike a typical talk that I give, which may be, I'm trying to inform you on a subject, I have some motives here myself, because like Hadoop with Python is kind of half-baked. So, I'm trying to push the ball forward by giving this talk, okay? All right. Okay, so me personally, my name is Don Miner. Like I said, I got my PhD at University of Maryland, Baltimore County. I did some machine learning stuff. Then I've been doing Hadoop stuff for the past 5 or so years. Pretty much only been doing Hadoop. And then I have my own consulting business where I do Hadoop and data science stuff. I just started it recently. Let me see. I live outside of Annapolis, which was really fun today. Took me like 2.5 hours to get here. I was planning on having dinner. So if you hear my stomach growling, or if you see my buddy leave, it's because he wanted to get dinner.
Just wait how long he's going to say when he comes from, when he goes to PyCon, how long it's going to take him to get from that.
Yeah, well, I think I would have rather taken a flight to Montreal than drive here. I think it's actually just about the same length. Yeah, so, all right. Any questions about me or what I'm going to talk about or anything like that before I get started? Alright. So the way this talk is going to look is it's very survey feeling. So I'm going to kind of bounce from topic to topic, spend a certain amount of time on each topic, and they're all kind of tied together but not really. I'm going to start out with an introduction to Hadoop. Since this is a Python audience, I'm going to make the assumption that you know very little about Hadoop. I'm not going to go into too much technical depth. What I'm going to try to do is I'm going to try to sell you on why it's really cool, why it's important. One of the reasons why I like Hadoop is because I really feel like it's important technology and it's been able to solve problems that haven't been able to solve before. And that's usually my litmus test of like, is this interesting or not? Like, has it been done before, yes or no? So I'm going to talk about Hadoop, and then I'm going to go through a list of topics of different ways you can do Hadoop with Python in particular. I'm going to kind of talk about what your alternative is from the Java perspective. Particularly, I'm going to talk about MapReduce, which is the most classic way of executing or processing data in Hadoop. I'm going to talk about Pig, which is an alternative to MapReduce. It's a higher level scripting language-like thing that interprets down into MapReduce. I'm a big fan of Pig, and how you can interact with Python with that. I'm going to talk about a library called Snakebite, which interacts with the storage system in Hadoop. And then I'm going to talk about HBase. HBase is a distributed data store that runs on top of Hadoop. And I'll talk about a little bit why that thing needs to exist. And then I'm saving the best for last, which is Spark with PySpark. Spark's kind of like getting the most hype right now. So I wanted to keep that last so you actually stay through the entire talk. All right. Any questions on the agenda? All right. Okay, so diving right into intro. So there's two major pieces that you need to really understand about Hadoop, and actually maybe only really one piece now, but there's execution and storage. Okay, and there's a separation of execution and storage. So back when Hadoop just started, there was only HDFS and MapReduce, but MapReduce has been, there's different options for execution environments now. There's like Spark that I mentioned, there's like Impala, Pivotal's Hawk. There's a few things out there that are kind of subsuming MapReduce's responsibilities, but the one thing that's kind of stayed the same is HDFS. And a little bit of history on HDFS. So HDFS was, the history of HDFS I think is really interesting. I don't know if other people think this kind of history is interesting, but Google published this paper called on the Google File System back in the early 2000s. I think it was like 2001 or 2002-ish. And it had all these weird properties to it, and nobody really understood why they were doing this. And everybody that read it was like, these guys are not telling us something, or they're just idiots, right? And nobody really thinks Google was idiots, so they just knew that they were missing a piece of the picture. So what the paper they had was this distributed file system that stored files. It's pretty obvious. But at large, it stored files in long, contiguous blocks. So you take like let's say I had like a 1 gigabyte data set. I'd store that data set into these 64 megabyte or 128 megabyte sequential blocks. So, and the other thing too is that you'll store 3 replicas of each block. Okay, so each block is copied 3 times. And then blocks are scattered all over the place kind of randomly. So the reason why this is kind of a crazy idea is that when you compare this to like a traditional storage device, like a SAN or like like a NAS or something like that, usually data is like striped instead of contiguous blocks. And then also too, you're using some sort of like parity bit paradigm instead of using replicas. Because replicas, if you think about it, is actually pretty financially irresponsible, right? I mean, if I want to store a terabyte of data, I need now 3 terabytes of disk, right? So people were kind of confused about this, and so nobody actually went and implemented it. And then they released the MapReduce paper, and then everybody was like, oh, okay, it all makes sense now, okay? So HDFS is the implementation of the Google file system that was implemented at Yahoo. And it follows the same thing. So it's got files. When you submit a file, write a file into HDFS, it splits it up into blocks, and these blocks are 3 of those blocks are randomly scattered across a cluster. This is done on commodity x86 hardware. There's like plain old hard drives. You don't even use RAID. You just put the stuff on there, okay? Commodity, to me, in 2015, means non-proprietary. Like, the Hadoop nodes that people are buying are like, 10, 20 grand a pop, right? It's not like you're... I have strung together... the worst Hadoop cluster I've ever worked on was 12 MacBooks. It didn't work very well at all. And, but so it'll work on that shitty hardware, but also too it'll work on kind of higher performance hardware. Does anybody? This is my only slide on HDFS. Does anybody have any questions? Seriously. Super important, but I only made one slide for it.
Isn't the replication optional?
Okay, so is the replication optional? So 3 replicas seems like kind of an arbitrary number, right? Well, the first thing, it is optional, so you can configure it to be more or less. So with 3 replicas, there's a couple of reasons why 3 replicas is kind of neat. So one is that I can now lose 2 nodes at once in short order and not be screwed. And actually, that's surprisingly common. So 3 nodes is good for a redundancy standpoint, where it's kind of a sweet spot. One place where replicas really help, now this will make sense again when I talk about MapReduce, is that the reason why the blocks are set up in long continuous chunks is because what MapReduce is going to do, and the other systems that use MapReduce, are going to utilize the fact that these are written in sequential, so you do less seeking on disk. So you're going to read more data. Now, the downside of this is that let's say I have like 18 MapReduce jobs running. All that data hitting the same drive is bad. So by having 3 replicas, you then spread out the load a little bit. So actually having 3 replicas is a really sweet spot for performance. When you switch to 4 replicas, you almost see no increase in performance. But if you go from 3 to 2, you notice a big difference. So that's kind of where people got across on 3. I have some people be like a little ballsy and run on 2 replicas. Or sometimes if you're doing a cluster upgrade, you need to shut down a bunch of nodes. Some people even run down to 1 and just hope for the best. But yeah, it is configurable. It's also configurable on the file level too. You don't have to set it for the entire cluster. You can say like, this data is less important to me, so I'm only going to have 2 replicas. This data is super important, I'm going to have 4. Yeah. Any other questions about HDFS? So we've seen HDFS scale to like, I think publicly documented something like 3,000 to 4,000 nodes. And we're talking about like close to 100 petabytes probably. So it's pretty awesome. All right. Any other questions on HDFS?
This is a leading question, but can I edit my files?
Yes. No, you cannot. So one of the big downsides of HDFS is that you can pretty much only create, read, and delete. So you can't update files, you can't edit files. And so the cop-out for that, well, editing files in distributed systems with 3 replicas is actually really, really hard. So what they did was this kind of cop-out where they were like, well, you just can't edit files. Why implement editing files when we can just make them not editable? So the answer to this question, and again, Hadoop is full of cop-outs, okay? Let me just get that out of the way, okay? So what my answer is when I have a customer that says, I want to edit my files, my answer is, well, you know what, why don't we redesign your use case or redesign the way that you're doing things today such that we don't have to edit files. So one example is calculating a bank balance, okay? So when you go check your balance or whatever and you see that you have like $37 to your name, editing that number in Hadoop is a bad idea. Like rewriting a file that now has added your $20 deposit is a bad idea. But why don't I just keep track of all your transactions, and if you ever ask me for your balance, then I'll just run a MapReduce job over this data and it'll take 20 minutes and I'll recalculate your balance, right? If you want to keep something up to date and you want to edit things in a Hadoop environment, that's where something like HBase would come in, which allows you to do updating of data on like kind of a cell level. Yeah. Is that satisfactory? Does anybody have any other questions about HDFS?
It's not a question, but I think NSA cares about what's in your files.
I'm sorry?
I said, like, it's not a question, but I think NSA cares about what's in your files.
NSA cares about what's in your files?
I'm just kidding. Please do it.
The NSA is a huge user of Hadoop. They have some very well-documented use cases, and they built the Accumulo database, which is pretty awesome. Anyways, I have an Accumulo sticker on my laptop, so I'm a fan of Accumulo. All right, any other questions about HDFS? All right, let's talk about MapReduce. So, MapReduce analyzes the data, and it's called MapReduce because there's a map phase and a reduce phase. And it's the way that it parallelizes things. So you're going to have lots of mappers and you're going to have lots of reducers, and individual processes are going to be running mappers and reducers kind of asynchronously from each other at the same time. Okay? And reducers run generally after mappers, but some of the reducers can start early. But the way that generally map and reduce work, and again, this is a very high level, you know, when I teach a class on MapReduce, it's like a day and a half, right? I'm trying to cut this down to one slide. Mappers in general are for like loading data from HDFS and parsing it. You know, if it's like CSV, maybe I'm splitting on comma. If it's text, maybe I'm tokenizing words. All kinds of things, right? I'm also doing any sort of like filtering, transformation, or parsing of that data. So if it's like a date timestamp in a format that I don't like, maybe I'll translate it. You know, if it's in text and I want to create some sort of Java object out of it, I'll do that here. And then I'm just going to output key value pairs. So what the mapper phase is doing is, for every record in your data set, it's going to run this map function that you write once. So I write a function, then the MapReduce framework runs that function on each record. Okay, does that make sense? So that is a very parallelizable thing, because each record doesn't care about the other record, which is what's called shared nothing. So basically, So there's a few interesting properties. One is I don't care in which order the maps run, right? Because I don't care about order. I don't care if this file gets processed before this file. I don't care if this file fails and I need to reprocess it. There's all kinds of nice things that fall out from this, okay? So the map phase is extremely parallelizable because I can just spread out the work more, okay? And typically one mapper is assigned to each split. I said typically, so if I had a gigabyte file that was split up 10 times, I might have 10 mappers run over this data set, and that's how I get parallelism, okay? Make sense? All right. So the mapper is going to write out this key value pair, okay? And you program this. And the key, there's this magic stuff that happens between the mapper and the reducer phase. And there's the combiner, the partitioner, the shuffle, and the sort, okay? Which you can go look up later. But believe me when I say, in between this phase, it groups all the data that was sent from all the mappers by key, okay? Into a group. So if you have a key that was output from mapper 1 and a key that was output from mapper 4, and they share the same value, they will be grouped together in this magic phase. Okay? Then the output of this magic phase is a bunch of groupings of the different groups. Groupings of different groups. Each group is kind of segregated from the others. And the reduce function is ran over all the values that had a particular key. Okay? So if I write, so for example, let's say that I wanted to count, or I wanted to, I'm McDonald's, right? And I have all this register data from all my point of sale systems. And I want to calculate how much money I made from every state. Okay? And I have all this receipt data. So I look at the receipt in my mapper, and I extract the state and the revenue associated with that receipt. Okay? The state will be my key, and then I have the dollar amount. Okay? In the reducer, I'm going to get a list of the dollar amounts of every single receipt in my data set associated with each state separately, and it's going to process each state together. Okay? So that's incredibly, honestly, once you start looking at it a little bit, hopefully you're not too confused, but it's pretty straightforward, and it's amazing how many awesome things you can do just by having that filter transform step in the mapper, then doing this group by on a key, and then doing some more additional processing in the aggregation step in the reducer. So you can do like aggregation, you can do search, you can do joins, you can do normalization, you can do like everything. Actually, one of the books I wrote called MapReduce Design Patterns is effectively how to use MapReduce to do things. Okay? So somebody was able to write an entire book on different things you can do with just MapReduce. Then also too, you can chain MapReduce jobs together and have the output of one MapReduce job go to the next. All right. Does anybody have any questions on MapReduce? Yeah.
What if you care about the order of your data? So like think of McDonald's example. Imagine you want to know like your profit in all states, but at any point in time of the day. Like how does my profit lunchtime, but like really fine grain. Like transaction by transaction. So I care that this one came before that one.
Yeah, so one really common pattern for time series analysis, which is really sweet, is so the way the reducer works is it does a sort. So it sorts on the key. And the reason why it does that is because when you sort something, all the things that are the same end up together, right? So that's why it uses sort. So one of the cool things you can do, which is what some of the things I do for time series analysis, is that you can exploit that sort to sort. It's called a secondary sort, where it's the sort on the values. You can sort the values by a certain thing. So let's say, so in your answer, if I wanted to do some sort of time series-based analysis on the data per state, I would still have the key be the state, but then I would have a composite key or value, where I have like a tuple, where the first part of the tuple is the timestamp, and maybe the second part of the tuple is like the value. And then I do a secondary sort on the timestamp, so that when I'm analyzing the data in the reducer, it's sorted for me by time, which is really cool. So that I can do like my normal time series kind of stuff. Actually, HBase as well is really good for time series analysis because HBase also stores things in a sorted way. So I've seen a lot of time series analysis done in HBase as well. So lots of good, if you just Google for time series, HBase or Hadoop should be good shape. All right. Any other questions about MapReduce? Yeah.
Is the key just a plain old Java object?
That's a great question. So Hadoop, the way it's implemented is yes, they're Java objects, but you have to implement a particular interface. So you have to implement the writable interface and the comparable. So and these are things that are defined. So writable basically defines a serialization scheme, and then comparable explains how to compare two things. And so as long as you implement those two things, you can have a number of custom ones, but Hadoop comes with a bunch of prepackaged like integers and strings and things like that. Yeah. But you have to use their objects. Any other questions?
So would it be accurate to say that some things are just fundamentally not map reducible, and that the reason that some of these other technologies exist is because...
Yep. Yeah. So that's a great history lesson too. So the question is, are some things just don't fit into MapReduce? And like absolutely. Actually, I think MapReduce only solves a really small problem. And what the problem MapReduce solves is large-scale batch analysis, right? So not everybody has large-scale batch analysis problems. I personally think those are pretty interesting. But so the first thing that people really realized they couldn't do with MapReduce was like streaming kind of analytics. So I have this like stream of data coming in, and I kind of want to process it in a relatively short order. Like I don't want to wait around like a whole day to process my data, because like common MapReduce pattern is maybe wait an entire day and then analyze your data, right? Maybe you wait a few hours. I mean, I've kicked off MapReduce jobs every 2 minutes too, but streaming was the first thing that people really noticed, like, wow, MapReduce is really bad at this. So a bunch of frameworks came out from that. That's where Storm came out. And then this whole notion of the Lambda architecture, which if you're interested in what I'm saying right now, you should go look into, which is this like complementary Storm plus Bash. Then Spark has a streaming architecture in it, and there was even systems like Flume and Kafka, which have a lot to do with also too data movement and ingest, but also can do streaming type things. So people kind of like decided like, okay, if I really want to do streaming, I'm going to do it in this other thing, complementary technology. The other thing then that people ran into, which they hated about Hadoop, was the fact that MapReduce is MapReduce and not like SQL, for example. So then there were all these guys that built SQL on Hadoop solutions. The first company was Hadoop, which got acquired recently, but I heard that that was not a good kind of acquisition. There's a thing called Hive, which is MapReduce-based SQL, but it's still kind of bound by MapReduce. Cloudera is a Hadoop vendor. They've implemented something called Impala, which follows a massively parallel processing architecture, which is a lot faster. And Spark also has a little bit better of an API to it. So there's this whole SQL on Hadoop thing. And then people were like, okay, well, SQL on Hadoop's cool, but I want my stuff to run faster. And that's where something like Spark came in. So Spark is kind of the big one filling that gap. So if you're a really large company and lots and lots of people, I've seen Hadoop clusters have like every one of those technologies running at the same time. When you're kind of a smaller group, like 3 or 4 people, like I think a lot of people start shoehorning things into things that shouldn't be, but it's kind of okay. So like in MapReduce, I can run my MapReduce job every, let's say, 2 minutes, and that's like pseudo streaming, right? It's not the best in the world, but it's better than having to support 2 different frameworks for a small team, right? All right. So yes, MapReduce does not do everything, and you will quickly learn what it's not good at. Any other questions? Yeah.
If I want to at some point do post-processing analytics of using data, are there patterns that I should follow to make?
Post-processing.
If I want to do, say, analysis of the most popular things that are hitting the site, or using patterns or patterns for data, are there ways that I should structure my data or store statistics about it so that I can have something post-process later? Yeah,
so the question was like, how does kind of post-processing fit into this? I'm actually not going to answer your question first because I think it's an important point. When you're using MapReduce, there's a certain point when MapReduce doesn't make sense anymore in your data processing pipeline, okay? So what I've seen people do a lot is they'll have this massive MapReduce job that processes a petabyte of data, then it outputs like 100 records. Let's say I was doing like the McDonald's case, right? I was processing like a petabyte of receipts, and then I'm only dealing with 50 states of output. And then like I've seen people run a MapReduce job over those 50 records just because that's their execution process system that they're working with. So what I personally find is that you know, a lot of times I can just write out the CSV. Like my personal kind of like what I like to do is I run my, when I flip over to something, I don't know if I should be embarrassed or not, but I really like Excel. So so my typical usage pattern is I'll run my large scale analysis over on Hadoop, and then I'll again, this is super embarrassing because this is the real world, right? I will then like copy and paste my Hadoop FS cat output, and then paste it into Excel, and then convert my pipes to columns, right? So like if that works for me, I don't know. Like so, there's also a number of like data formats that you can use. So outputting to JSON is not ridiculous. The Avro format is kind of like a good overall format. So universal data formats are more important when you're dealing with, or when you're working with other people, I think. Does that answer your question? Yeah. Any other questions? This is good. I may not even have to give the rest of my talk. Just Hadoop Q&A, right? Any other questions? All right, cool. All right, so then there's this whole other thing called the Hadoop ecosystem, okay? So the way you should look at it is that HDFS is this kind of underpinning of this whole thing. And then there's all this stuff that's built on top of HDFS, okay? Or things that interact with Hadoop. And I can try to categorize them a little bit. There's nobody that keeps this official list of ecosystem. It's just this thing, you know, that people are like, oh yeah, that's part of the Hadoop ecosystem, but I don't see why. But so there's, first of all, there's higher level languages like Pig and Hive. I'll be showing you guys Pig later. Hive is a SQL thing. HDFS data systems like HBase and Accumulo. So HBase and Accumulo, like our friend over there mentioned, you can't edit files. HBase and Accumulo were kind of implemented to kind of solve that problem because HDFS was bad at that problem. And HBase and Accumulo are based off this paper written again by Google called Bigtable. And Bigtable solved this problem for them as well because they were using a GFS MapReduce kind of thing, and they were like, well, we have this other problem, and so now they have Bigtable. So pretty much the story is with Hadoop, almost every Hadoop project started as some Google paper. And like the Google paper is like super light on details and like, you know, very hand wavy, and then some group of engineers just try to go out and implement it. So Google, in a lot of sense, in this whole industry is like kind of like the word of God, right? Like they state like we have Google file system, and then like we have MapReduce, and then there were some guys at Yahoo who were like, oh shit, we need to go implement that so we can be as good as Google. And then they don't interpret the word correctly, right? I gave a talk on Accumulo in New York a couple months ago, and there were some Google guys in the audience. I didn't know there were Google guys at the time, and they kind of came up after the talk and were kind of effing with me a little bit because they get to play with Bigtable at work, you know. And, it's not quite perfect, you know. You're never as good as what they were doing. So, anyways, the analogy just keeps going. There's also these alternative execution engines other than MapReduce like Storm and Spark. And then you've got these close friends which have usefulness outside of Hadoop but are used typically. So Zookeeper now is like used all the time, all over the place. Zookeeper is like one of the coolest technologies ever, by the way. Like it may be even cooler than Hadoop, I'm not sure, but it's less useful, but it's definitely really cool. It does like distributed syncing and locking and things like that. It's a good framework for building distributed systems. Flume is this like data transfer thingy. Avro is a data format. Kafka is like this pub sub thing. And there's like this long list of things that are considered part of this Hadoop ecosystem. Okay. Are there any questions on the Hadoop ecosystem? I just want you to know that Hadoop's not just. It's almost like saying. I heard somebody say like, you know, when somebody says they're using Hadoop, it means that it's almost like somebody telling you they use Linux, right? When you say you're using Linux, it's not like I'm just like walking up to my computer and I dirtle with the kernel a little bit, right? And like I log into the system and I do things with Linux, right? It's the same thing with Hadoop. When somebody says they're using Hadoop, it means that they happen to have a cluster that's running Hadoop on it, but they're doing all this crazy crap with like HBase and Pig and Spark and all that stuff. Okay, that's what using Hadoop means. It means using HDFS, probably MapReduce, and then this ecosystem stuff. Okay, all right, make sense? All right, moving along. So I'm going to go into. I have a list of cool things that I really like about Hadoop, which are trying to sell you on why this is important technology. So the first one is linear scalability. So and not only linear scalability, but scaling out linear scalability. So if you think about pre-Hadoop, and kind of not pre-open source software, because open source software has been around for a long time, but when you had like a serious data problem, that's when you called like Oracle up, or Teradata or something. And a lot of these solutions, they all scaled up. So you're like, well, I ran out of space. I need to call Oracle and like basically like sell some of my children in order to upgrade my database, because now they have you, right? Because you've got like millions of lines of SQL that is proprietary to Oracle, and you just need like just a little bit more data, just another terabyte. And they're like, okay, well, it's just going to cost you so much money. So that's what scaling up means. So Hadoop is, first of all, scale out, which means that I can kind of tack on to my cluster as time goes on. And then it's also linear. So what does linear mean? So in general, like let's say 80% of the time, 90% of the time, if I have twice as many computers, so I'm not sure if this is clear yet, but Hadoop is a distributed system that's running over several computers, right? If I have 100 computers and then I go upgrade my cluster and buy another 100 computers, things should take about half as much time. Okay? If today I have a petabyte of data and I'm expected to collect another petabyte of data this year, jobs that I have that run over that entire data set, if I have a job right now that takes me a day, it's going to start taking me 2 days. Okay? So if I go to my management and say, well, your MapReduce jobs are going to start taking 2 days now. Well, that's not good. Okay, well then buy me another 100 computers. So it's very nice on the math, right? So that's actually really important. There's several companies that buy new Hadoop nodes every year to scale with their expectation of how much data they're going to collect that year. I've also done proof of concepts with Hadoop where we've set up like a 5-6 node Hadoop cluster, and then just did the simple math. And like, well, we did this with 6 nodes, so if you really have 100 times more data, you need 600 nodes. You'd be surprised like how close we get. It's really awesome. So, all right. And then also too with the advent of like elasticity. So if you're using like Amazon Web Services, EC2 kind of stuff, if you're like, man, my job is running a little slow, just add more EC2 nodes. All right. Any questions on this linear scalability?
Can you explain data locality?
Oh, yeah, I have that in explanation reports. I forgot to explain that. So, yeah. Data locality is really important for understanding linear scalability. So, what data locality is the concept of processing data where it is without having to move it over the network. So, and this is what MapReduce job does. If you think about it, a MapReduce job has mappers, right? Hadoop is going to instantiate the map process, or it's going to try, with a lot of success, on the same computer in which that segment 64 megabyte or 128 megabyte chunk is residing. So when that process starts slurping the data off disk, it's pulling it straight off disk. It's not going over the network. Okay? Now, well, why is that so important for data locality? Or why is data locality so important for scalability? Well, pretty much the one thing that they haven't been able to figure out how to make linear scalable is networks. Okay? So I can't just buy eight times as many switches and get everything to work better, right? And even bonding links doesn't really help that much because there's overhead about translating the bonded links, right? So what this allows you to do is over just a plain old network on your cluster, there's almost no network utilization at the beginning part of a MapReduce job. Okay? So what that allows you to do is, let's say I have 40 petabytes of data and I run a MapReduce job. Those mappers are going to run over those 40 petabytes of data, and if you're watching like Ganglia, which is like a monitoring system, you'll almost see almost no network chatter at all. Just like super cool. And that's what data locality is. And actually, that was one of the big contributions I think that Google made in their papers. Like, hey, data locality is really important. All right. Any questions on data? Yeah.
Somehow you would have to configure that, right? Depends on what you're trying to do, right?
What do you mean?
So if you want, back to the technology example, if you want every state's data on the same computer, so how do you...
Yep, okay. So there's a difference between, you're catching on something. So mappers, the way a mapper will work, right, because that's just record by record, the mapper will ask HDFS, say, hey, where is this data? And then it'll go instantiate the map task on the data node where it is. But on the reduce side, where I'm then post-aggregation, like Maryland data is going to be from lots of different places, right? So what happens is that, yes, most definitely, when you're watching stats on your cluster, when mappers start sending data to the reducers, you start seeing network utilization go up. So there are types of MapReduce jobs you can do that are going to peg your network. But the kind of cop-out here is that the mappers send data over time as it's processing over the network to these, and then the reducers kind of pull the data from the guys that produced it. So it's kind of spread out very nicely. And it's also point to point. So if I have 1,000 reducers, each 1,000 of the reducers is pulling thousands of bins from across the entire cluster. So it spreads out the network usage. So the network is still important, even with data locality. Yeah. Any other questions? All right. Cool thing number 2. So, so kind of contrast here. So schema on read is versus schema on write. Schema on write is like Congress. So when you're developing a policy, okay, you have to talk a lot about it, and then you have to get everybody to agree, and then you have to go implement it. And the best thing about this whole process is that almost nobody ever gets it right on the first try, right? So before, when we were dealing with the relational databases, you'd have to plan out your ETL, which is your extract, transform, load, which is basically how I'm going to load and process my data so I can put it into my database. You can't just put like receipts into a SQL database, like I need to normalize it and all that crap. I need to do schema design, so based on the queries that I'm going to have, these are my foreign keys, and these are my tables, these are how I'm going to set up my indexes, right? I mean, when I was working on our DBMS projects, you could be months before you actually inserted any data, okay? And you're doing like data studies, you're measuring cardinality on columns, it's crazy. You're doing all this work, and the crappy thing is you spend all this time planning, and at the end of the day, it wasn't good enough, and you end up redoing the entire thing anyways. So what Hadoop does, and what I think a lot of kind of general concept behind a lot of those NoSQL databases and data stores, is that with Hadoop, what you do is you load the data first, before you know what you're going to do with it. And then the nature of the data, what I mean by the nature of the data is this JSON, is it a format? And even then I can have data that's serialized in different ways, right? Am I storing an integer as a byte, as bytes, or as ASCII? Is it Unicode? Like, right? There's all kinds of issues. But I interpret the nature of the data when I'm processing it. So the MapReduce job is the one that's saying, this is the price on the receipt. This is, the state. I didn't do any of that up front. Now, this has some really serious implications. So one is I can keep the original data around. Now that's important because back in the old days, or I mean it's still done right now, with schema on write, a lot of people didn't have anywhere to put the raw data. So once they ETL'd it and they wrote it into the database, they deleted all the original data, which is bad if you decide to change your mind because, or you had a bug in your processing, right? So that's bad. Keeping the original data around is good. Having multiple views of the same data. So one kind of canonical example of this is that, so based on some sort of like NLP kind of processing thing I may be doing, it may make sense for me to be reading data on a per line basis, or maybe I want to process data on a sentence basis, or on a paragraph basis, or on a chapter basis, or on a book basis, right? So like if I'm processing information about books, right, I may want to process the entire book together on one map task, right? So I can kind of, so in a way, based on these different views of the data, I can interpret different nature of the data based on stuff. Another example is like image analysis. So maybe I have a bunch of JPEGs that I'm storing or something like that, and I want to analyze it. Maybe I'm doing some metadata analysis, like I'm just seeing like, oh, who took the picture, some of the like tagged information on an image. Or I could have like a MapReduce job that's actually analyzing the image, right? So I can have different views of the data even if the raw data is the same. I can work with unstructured data sooner. Unstructured data is like raw text, things that have less structure, instead of having to do all this processing up front. And then the other thing too is I can store it first and figure out what to do with it later. So a lot of people don't know what the value of their data is. So when you're saying like, hey, we're going to build this big database and store all this data in it, and somebody says, well, what's the ROI? And you're like, well, I don't know, right? We haven't built it yet. It's like a chicken and egg thing, right? So with Hadoop, what you can do is you can store it, and then you don't have to worry about ETL and all that stuff. You can store it and then start processing it over time. So when I first started a Hadoop project, one of the first things I try to do is set up the data flow so that I start loading data. And then as soon as I have my first MapReduce job written, let's say a week or two, I already have a week or two of data. Right? So I can write all these MapReduce jobs after I've loaded the data, which before with scheme on write, they kind of go hand in hand. This is super huge. I mean, I try to explain this to interns sometimes, and they're like, because they haven't had to deal with like the way it was with RDMSs, right? So, anyways, super important. The next one is transparent parallelism. So, what you'll see in some of the MapReduce code I show you later and some of the other code is that you don't code anything about parallelism. Okay, so in some of the earlier like MPI clusters and Beowulf and things like that, it always kind of bled through even just a little bit. Like you knew you were on a distributed system. Okay, with Hadoop, when you're writing map and reduce functions, you don't really know. You're like writing this map function, you're writing this reduce function, and then you like submit it to the cluster. Like I mean, I don't really care if it's running over like 30 petabytes or like a gigabyte. Like the code is exactly the same. So you don't care about scalability. You don't care about like any sort of message passing or RPC or you don't care about a lot of these things. You don't care about fault tolerance. I'm not baking in fault tolerance into my code, right? If my task fails because a node goes down, the framework handles it for me automatically. So this is all stuff I don't need to worry about. Okay. Now, and that, again, is super important. And this is why I think Hadoop has become really important. I mean, distributed systems have been around for a long time. But the reason why Hadoop has gained mainstream appeal is because I can give a developer that knows nothing about distributed systems and say, like, here's some example MapReduce code. Go try to, like, do something with this. I mean, I've had new engineers straight out of college that are running analytics on, like, a petabyte of data, and they have absolutely no appreciation for what they're doing. Right? All right. So the next one is unstructured data. I'm not quite sure sold yet, but I think a lot of people would argue that Hadoop kind of motivated people to analyze unstructured data more. And what I mean by unstructured data is we're talking about like text or media, so like video or, so I've seen video being analyzed, I've seen audio being analyzed. This is log data. Log data is a pain in the ass, right? Before that was all Perl, I guess. And log data is a pain in the ass because different lines can mean different things, right? So like this log message is like a failure, this log message is like a, some other sort of message, right? So I think Hadoop really helped analyze that data, but I think people were trying to analyze that data. They were starting to get more serious about analyzing this data. So I think it might have been coincidental that maybe these two things went hand in hand, but Hadoop is really good at this because at the end of the day, you're just writing Java, or as you're going to see, you're just writing Python to just process this data as it is in place. Okay? We've even seen people write MapReduce jobs in Perl. I don't recommend it, but all right. Is there any question left on why Hadoop is cool? Does anybody want me to continue to try to convince you? All right. So, kind of why Python here? Okay, so again, Python versus Java. I don't actually write down. I post these things on SlideShare, so I don't want to write anything too inflammatory in writing. But I'm not a huge fan of Java, and I never have been. And I've had a long philosophical conversations with some Java users, and I realize it's like a personality thing. I think I'm more of like a data hacker kind of person, where I like to iterate on my stuff very quickly. I prefer ease of use over performance. There's a number of things why I think Java is good, or Python is a good language for me, and why I hate Java. So some of the benefits I think to anybody is, and it's not necessarily a benefit, there's pros and cons. So the first is compiled versus scripting. Okay. Now this is pretty subtle, but when I'm writing Java MapReduce jobs, I have to compile them. Okay. Now let me explain to you the pain. Okay. So you don't write just like. So I have my cluster over there. I don't have like Eclipse open in X window right on my desktop. I'm writing MapReduce jobs on my local machine in Eclipse. Okay. And then when I'm done running over my sample data, I then compile that thing into a jar, and then I copy the jar to my cluster, and then I run the jar. Okay? And then I realize there was a problem, so I go fix it, recompile the jar, and I put it up to the cluster. Oh, Bob's having a hard time today because he forgot to upgrade his Hadoop on his local box because we updated the cluster. So then now you have version mismatch problems between developer workstations, and compiling is a huge pain in the ass. Okay? Then you're like, well, I'm going to solve this problem with like Jenkins and like build systems and stuff, and then you just paid some developer like probably 1,000 hours to go to implement this like Jenkins automatic continuous integration DevOps thing, right? So, anyways, so that's my pain, right? Scripts, on the other hand, it's a lot easier to edit them in place, first of all. So like if I have a small change that I want to make to a script that's on the cluster, I can just go edit it in place and update it. That's a little cowboy, but it is what it is. The other thing too is that scripts are more resilient to underlying system changes. So like if I update my version of Python, for the most part, as long as I'm not deleting between 2 and 3, it should just work, right? So there's backwards compatibility. I don't need to recompile things to make sure that they're working against previous libraries and things. And I hate Maven. I just don't understand. Like I probably spend. I think on average, on like a good sized team, people probably spend anywhere from on Hadoop projects, probably anywhere from 5 to 20% of their time debugging no class def and like version mismatches because of Maven. And actually Maven makes life easier, but it still doesn't do good enough. So anyways, I'm ranting a little bit too long. The other thing is that there's a lot of libraries in Python that are like first class. So like NumPy, SciPy, scikit-learn, pandas, like these guys are like, that stuff, some people are kind of so narrow-minded and they're like Python, like I only use Python, they don't really think about it. Those libraries are actually like world-class, like better than other options in other languages. So like, if I'm serious and I want to use scikit-learn, even if some people use scikit-learn in Python, even if they're not Python programmers, because they want to use scikit-learn, right? So by having Python with Hadoop, then I can use some of this data analysis libraries, which are kind of cool, right? And then integration with other Python things, which is kind of cool. But Java has integration with Java things, so. All right. So why not? I think everything I'll talk about today is slower than its Java counterpart. And it's not just because of the traditional Java versus Python. It's because Java is its native language, so whatever you're doing in Python, there's some sort of translation. So you get performance. The other issue is that Python, since it's this non-native supported thing, it's always maybe sometimes a step or two behind. So if new APIs are implemented or new protocols are implemented, sometimes the Python libraries are lagging behind a little bit. And also too, there's it's a much smaller community, and the main vendors, Cloudera, Hortonworks, Pivotal, and MapR don't support really the Python stuff. Which is, kind of shitty. So you're kind of on your own. You're going to be doing a lot of like downloading from GitHub and hoping like setup.py works, and there's tons of that, right?
Is performance really a problem? It seems like the definition of an I/O problem.
Yeah. So the question is performance a problem? And I think in a lot of cases it's not, right? Which is why I try to use the Python with Hadoop stuff as much as I can. There's been, I'll talk about this a little bit when I'm talking about Mr. Java a little bit, but people have like measured like 7x like performance difference, which is a pretty big deal. But in some cases, like, so my job takes like 10 minutes instead of like 6 minutes. Is that a big deal? That's not 7x, but like sometimes the fact that I was able to get the job done faster and was able to use like NumPy, like, is so much worth it for me. And also too, you can always solve a performance problem by buying more nodes, right? So, if I ever had a manager tell me, he's like, we really want you to start writing Java MapReduce, I'll be like, all right, that's fine, but you might want to hire another one of me because my productivity is going to go to about half. You'd probably be better off just buying another 200 Hadoop nodes. So, solving problems with money is I'm a huge fan of that, as long as it's somebody else's money. All right. Okay. Any questions on this so far? All right. Let me try to speed through this a little bit quicker. So now starts this kind of survey of different Python and Hadoop stuff. First one I'm going to talk about is a lot of I've always heard it called MR job, but I heard somebody call it Mr. Job one time, and I just thought that was awesome. So, so I call it Mr. Job now. So Mr. Job came out of Yelp, and apparently all their MapReduce runs on Mr. Job, and basically it lets you write MapReduce jobs in Python. And it was open source and has active development. So, like, if you go on the GitHub page, like, they have probably commits from a couple of hours ago. What it does is it wraps this thing called Hadoop streaming. And what Hadoop streaming does is it wraps the MapReduce framework, the Java processes, through standard in and standard out. So what Hadoop streaming lets you do is it lets you write this arbitrary script or program or something that takes standard in and a specified tab delimited format and it writes out in a tab delimited format. And then you can write MapReduce jobs in Perl or Lisp or where the hell I mean Bash, right? So what Mr. Job does is it takes your Python program and you're going to write your Python program in terms of map and reduce, and then behind the scenes it's going to do the serialization stuff to Hadoop streaming. Okay. Mr. Job is very well documented. I mean, as an open source project goes. And one thing that's really cool about it is that it has like so Yelp is a big user of EMR, which is Elastic MapReduce, which is Amazon's MapReduce system, which has some like nice like Hadoop as a service kind of things. And it has really tight integration with it. So you can just kind of say like, hey MapReduce job, I want you to run on EMR with these S3 buckets, and it just like magically works from your local workstation, which is like super cool. So word count is the canonical example. I think in retrospect, I wish I had added what the Java word count program looks like. But the Java word count program is maybe about like 120 lines of Java code, and it's like almost all boilerplate. So this is Mr. Job. So I'm going to point out a couple of things here. So at a very large level, you see that I have a class here that's inherited off of this Mr. Job object. I've got this like regular expression thing going on here. And I've got this mapper function and reduce function. I'm using yield. Okay. Does anybody know what yield does? Does anybody not know what yield does? I should probably explain that, right? Okay. So in Python, yield is a Python thing. So in Python, when you have a function and you yield something, it's almost like returning. But what you're saying is I'm returning an item in a list, effectively. I'm simplifying. It's not really a list; it's a generator. But what it allows you to do is return several things in sequence in a function. So the reason why it's being used here, it's not being used in a traditional sense. What this is allowing you to do is it allows you to output several things from a map function. So if you look here with this mapper, this for loop, and then it's doing a yield, it's almost doing like a mini return for each iteration of that for loop. Okay? So kind of glossing over it. It's actually a pretty complicated subject now that I'm trying to explain. All right. So let's take a look at this thing. So let's say I'm doing word count. Word count is going to output, I saw this word this many times, okay? So I take this first sentence, and like I said, the map function gets applied to every single record in your data set. In this case, I'm going to do line. So every new line is a separate record. So I take this sentence, it goes into the mapper, and if you look into this thing, what I did was I have this compiled regular expression, which is \w, which is basically words, and also quotes, single quotes, and then I'm going to tokenize on that. So basically I'm going to pull all the words out. And then I'm going to yield the lowercase of that word, comma 1, a tuple. Okay? So what the output of this thing is this series of yield statements, the one, quick one, round one, fox one, etc. Okay? Everybody follow? Alright. So let's do it again. This is a separate sentence. This map function then it decomposes that sentence again and writes out a little bit more. Okay? Now remember, maps don't care where they're running, right? They could be anywhere. This could be a different map task. I could have multiple map tasks running at once. All these guys are just all running at once, generating a ton of yields. Okay? Alright. So then the reducer, and if you remember correctly, the reducer grouped everything by key. So if you look here, the word is the key and 1 is the value. Okay? So what I'm going to do is the reducer takes a function where it has word is the first parameter and counts as the second one. I should have mentioned, the mapper has 2 parameters. Well, it's got self because it's in a class. I have an underscore here because I'm not going to use it. the first parameter is usually the byte offset of the data set you're loading. So in this case, byte offset to me isn't useful. The second one is the line, which is the text, which is useful. When I'm looking at the reducer, the first one is the word, which is the group that I was grouping on. And then the counts is going to be a list, or it's actually a generator, a list-like object of the counts that had that key. So if I saw a dog 6 times in my corpus that I just analyzed with this MapReduce job, I'll see 6 ones in here. Okay? And then I sum those ones, and then I yield again to output. Okay? And then that's what comes out of my thing. I see cat, and I saw cat 8 times. Okay? All right. So this counted a bunch of words in my corpus. You can do a whole ton of other things with this, right? So now I could have ran this MapReduce job, this word count over a petabyte of data, a megabyte, whatever. And it's still the same code, which is really cool. Okay. Does anybody have any questions about this job? Yeah.
This is a more general question about this. Is kind of an example you see a lot. You always kind of yield word 1. Is there a reason you might want to like just go ahead and process the line yourself? And you like E7 and cat 2?
You guys are super sharp because I'm trying to be quick about this whole talk. But you guys are actually asking the questions that are really interesting. So there's an optimization step in MapReduce called the combiner. And what the combiner does is it does a mini reduce on the map side. Okay? So if you think about it, I may see the word cat, let's say, 3 times in one map task. But I don't want to mess up my behavior or the fact that I don't want to have to keep like the fact that I saw cat multiple times in cache or in memory. Like I just want to give it to the framework and forget about it, right? So what the combiner does is it does a mini reduce on the map side. So what it'll do is it'll take all the map output for a particular process and do the reduce. So in this case, it'll reduce it down to cat 3. And then it sends cat 3 to the reducer. So cat 3 is 3 times as more efficient as sending cat 1 3 times, network-wise. So typically in word count, you would generally run what's called the combiner, and you'd use the same code as the reduce. So in reality, you're not getting 1s here. You're getting like 1s and 5s and 7s and stuff. So that's in general why I'm using 1s, because I'm utilizing the fact that I've got the combiner running. The other thing too is that a general good practice with Hadoop is you want to use as little memory as possible. So if I wanted to process the entire document and count how many times I saw cat and stuff, I had more stuff in memory. The reason why I want to reduce memory is a couple of reasons. One is garbage collector is slow, and so if you give it less work to do, your job will run faster. And then also too, when things are at scale, memory assumptions don't necessarily work all the time. So like, yeah, this fit in memory on my local box, but then when you go run over a petabyte of data, it blows your heap and then everything fails. So in general, you want to keep it as little transient memory around as possible. And that's one of the other reasons why you're using 1s. I'm letting the framework count it instead of my code. All right. Yeah.
So this gets compiled and sent over to...
So the way this works behind the scenes, so this Python script runs, okay, and MR job, or Mr. Job, I keep saying MR job, I want to say Mr. Job. Mr. Job will take that Python script and then I think it's not really compiling it, right? But what it does is it turns this code into this thing that writes standard in and standard out, okay? And then Hadoop streaming is a compiled MapReduce job. So, and it's a jar. So Hadoop streaming thing is a jar in your Hadoop distribution. And it passes these scripts that it generates to the Hadoop streaming thing. So there's no compilation involved because Hadoop streaming is almost like an interpreted MapReduce framework if you want to look at it that way.
So I was just wondering if this means you've got a Python running on every node.
Oh, you most absolutely do, yeah.
Oh.
Yeah. So that's actually a good point too. You need Python running on every node because Python processes are running on that node. The second thing too is any sort of library that you're using, like NumPy or something like that, needs to be installed on all the nodes as well. There's actually some utilities for automatically shipping libraries along with your code. But you most absolutely, because it's running it locally as a separate process. Yeah.
I'm wondering where the second argument in reducer counts is coming from. Is it baked into the Mr. Job class?
Yep. Well,
or is it
yes, it's interpreting what streaming is giving you, and streaming is giving you the data group by key. So that's the list of things that had that key. So yes, it is. Between the map and the MapReduce is very magical, but there's a lot of work that goes on there. Yeah.
So this is my script that's on my cluster, and it's run.py, which run Python run.py, and it looks for like the Hadoop home environment variable.
Yeah.
That's cool. Second.
It looks up the Hadoop conf. You need to have the Hadoop confs in your path.
Okay.
I think it's like it looks up like Hadoop.
So Hadoop binary needs
yeah.
to be okay on your path.
Yep.
And then the second follow-up question on it. I've used Hadoop streaming with Python a lot, and my very favorite thing about it is I can like cat a local text file into my mapper and see my results and standard out testability.
Yep.
Like, there's no easier way to test it.
Yep.
Is there kind of an analogy for this job?
So the kind of question was, he's done Hadoop streaming before, and one of the cool things about Hadoop streaming is that you can cat a file and pipe it into your mapper code, and it'll just like work, which is pretty cool. So you can test it locally. Mr. Job has a local development framework. So it has 3 modes. It has local, EMR, and Hadoop. So in local mode, what you do is you pass it a list of files or a directory, and then it runs over those files. And it's better than catting because it's actually simulated. It'll have like different mappers for every file. It works really well. Yeah. I also used to do Python in Hadoop streaming, and I like this much better. Because the reducer logic in Hadoop streaming is kind of awkward sometimes.
Cool. Thanks.
Yep. And also, too, any parameters and things that you're using for Hadoop streaming, you can pass to MR Job as well. All right. I was going to give a demo, but I'm trying to move along. So here's some other options. So Hadoop streaming we've kind of mentioned a couple times. It's a little bit more manual, but it is faster. There's been some other libraries, there's Hadoopy and Dumbo, but I checked the GitHub, and they haven't been like updated in a couple of years. Hadoop is a main competitor. I'll talk about Hadoop in the next slide. Now, this is the he's been talking about all. I like everything he said so far. So if you look at Mr. Job here, a comparison to Java. So this Java job ran in like 1,000 seconds. Mr. Job ran in 7,000 seconds. So 7x slower. Hadoop streaming was 1.5. And if you look at the reason for it is that Mr. Job's serialization scheme, when they first implemented it, was really, really, really bad. So that overhead cost was due to a lot of serialization. It was doing like JSON serialization or something behind the scenes. It was really ugly. So if you plug in like one of the better serializations, apparently the performance is supposed to be a little bit better. But at the end of the day, like Java, since it's actually incredible. The standard in and standard out interfaces are like one of the biggest bottlenecks in this whole thing. Meanwhile, in Java, you're kind of talking directly, so it's a little bit faster. Oh, it's a lot faster. So if you're concerned about performance, then this would be bad. I think the other thing too is what I'll do is I'll run it. I'll write my job in Mr. Job or Pig, which I'll show you guys later. And if it works fine to everybody's like pleasure, then I'll just leave it. If people are like, this isn't fast enough, then I'll go implement it in Java. So like, because, I mean, it took me like, maybe 10 minutes to write this MapReduce job in Python. And then if it works fine, then who cares, right? So, I don't know. That's my cop out. So, Hadoop is another one. I really want to try Hadoop out. It seems pretty promising. It has an active community. It's built by this like research lab in Italy. And it uses a different strategy. It uses this thing called Hadoop pipes, which is this like C++ interface into Hadoop, and it's apparently like a lot faster than Mr. Job. So I want to try it out. The API looks like similar, so I can't really tell. I haven't used both enough to really tell you which one I like better. They both seem reasonable, right? All right. Hadoop word count is a little bit similar. Hadoop, you have like mappers and reducers, but they're just functions. They're not part of a class. And then you have to use this Hadoop executable, which kind of wraps the whole environment. That's a big difference. Okay. Does anybody have any questions about Python plus MapReduce or MapReduce in general before I move on to the next subject? Yeah.
Go back to the table. It might have to do with I'm seeing the performance hits and the size is smaller. Is that generalization I can make? I was just wondering if starting up all those Pythons going to happen fast?
It's not nearly as bad as the JVM. So, like, starting up with JVM is like the biggest overhead of all time, right? So, I don't think starting up a Python interpreter is really killing you. So, if you're really interested in the performance, the kind of canonical piece on this is this Cloudera blog post that was posted in 2013. If you just Google for Python Hadoop Cloudera, like this blog post will come up, and there's a more up-to-date slide deck at the bottom of the thing. But they talk a lot about why performance is bad. But also too, this is out of date. Like this was before when they were using the bad serialization scheme. It's still slower than Java, don't get me wrong, but should be a lot better. All right. So the next thing I want to talk to you guys about Pig. You know what? I'm gonna kind of go a little bit faster here. So Pig is a really cool language, and it does like data flow kind of transformations on data. So it's higher level than what we were seeing before with MapReduce. I hope you get that point across. I'm not going to try to explain how Pig works, but basically I load data, then I transform it with like a for each, and then I do some tokenization, and then I do grouping, and then I do for each. And then behind the scenes, this turns into MapReduce jobs. Okay, that's pretty cool. So one of the things is that when you're doing individual processing on little like individual pieces of data, Pig's not great at that. Pig's good at like macro things, right? Like moving data around, transforming things into large scale. But when you're looking at like a particular character array and you want to do some processing on it, that's when you want to dive into a user-defined function. And you can write those in Python, which is great. So here's two examples. Here is like, for example, there's no built-in function for reversing a string in Pig. Okay. So what you'll do is you'll write this like simple Python function. Its output schema, this is a decorator for those of you guys that haven't seen it, telling Pig what is Pig's statically type. So you'll tell it like what its type is, the output type is. And so I'm just reversing a string here and then returning it, and then I can use that in my Pig script. I can also do fancier things. So Pig has this notion of a bag, which is like a nested list, which is the output of a group by. So when I'm grouping by, I get a list of things that have that grouping key. And then you can do operations on bags. So for example, this is like concatenating everything in a bag into sorting the bag and then concatenating them by height. Something I've done. So I would say that typically when I look at a new problem, my favorite way of solving the problem is Pig plus Python. So Mr. Java is pretty cool, but Pig solves a lot of like high-level problems for me with this kind of language. It lets me get some macro things done very quickly. More complicated things too, because this may spawn off like 4 MapReduce jobs. And then the Python UDFs allow me to do some cool stuff. Now, the bad thing is that the native UDF framework for Python uses Jython. Okay? Now, Jython is a Python interpreter written in Java, which makes sense because Pig's written in Java and Hadoop's written in Java, and that's all great. If I run Jython, then I never have to leave my JVM. Now, the bad thing with Jython is that it's basically impossible to handle any of the C binding stuff. Okay, so anybody that's using like any of the C stuff is basically out. So the big one is NumPy, right? So like NumPy arrays underneath are all C arrays, right? So the problem here is that basically any library that's built off of NumPy, which is basically everything that I care about, is out. Okay. And then also, too, your mileage may vary with other libraries, too, with Jython. I mean, Jython's not super supported. Things sometimes don't work. So there was a group that was like, well, I don't like that. So what they implemented was a C Python binding. But what it does is it starts a Python process off the side and then streams the data to it and then pulls the data back. So you've got this like very bad serialization. Again, serialization and inter-process communication overhead, and it's a lot slower. But if I need to do some NumPy stuff, then I'll use NumPy stuff. So what you'll see a lot is that like I'll have stupid stuff like reversing string in a Jython. You can use these intermixed. So I'll do stupid things like this in Jython, and then I'll kind of like compartmentalize all the NumPy stuff that I'm doing as the C Python stuff. Okay? And these things are super easy to write. I mean, it's really easy. It's really good. All right. Any questions about Pig? If you're really interested in Pig, one book that I really like is called Agile Data Science by this guy Russ Jernigan. Agile Data Science. And it's books by Russ Journey, who's a really interesting guy also too. But it's one of those books where, has anybody read the book? Okay. So my take on the book is, after reading it, it wasn't terribly useful, but it was fun to read. So like, and
It's like his Twitter.
yes, and him in person as well. It's a fun book, but the reason why I like it is because he has a lot of these. He's a big Python user. He's a big Pig user. And he uses a lot of these technologies in a really interesting way. And how you should be using them. So if you wanted to kind of take a look at somebody who likes Pig and Python and like see what their day is like, go read Agile Data Science. All right. So the next thing I want to talk about was Snakebite. So Snakebite is a HDFS library. So it interacts with the storage piece of things. So it's pure Python, and unlike all the other things we've talked about, it natively talks to HDFS, which is awesome. So it's not using any sort of translation layer or anything. And Snakebite is the one thing in this entire presentation that is better than its counterpart for the most part. Okay? So one of the things, so when I use Hadoop, when you use Hadoop and you're using command line utility, you do like Hadoop FSLS or Hadoop FS like cat or whatever, I have all these commands that I run. The way it's implemented is it basically spins up a JVM every single time I type in a command, which is super annoying. There's like ways to get around it, but for the most part, that's how it works. Okay. So every time I type Hadoop FSLS, it takes like a second to run. So these guys at Spotify, they have this processing framework called Luigi, which does like workflow processing and stuff. I mean, Luigi is really cool in its own right. It's written in Python, but really inconsequential. It's really useful for like, I have these prerequisites like, hey, if I have this much data show up in this directory, I'm going to zip it all and send it over here, things like that. And what they ran into was that they were wrapping shell subcalls, like they were calling popen to Hadoop FSLS, and it was taking like a second every time. And so their workflows were like bottlenecked by JVM spin-up. So what they were like, well, you know, if I have the Snakebite thing, which will do it in Python, the Python interpreter spins up a lot faster. So when you use Snakebite, you can interact with HDFS a lot faster. The other thing that Snakebite is useful for as well is interacting with HDFS through Python scripts. So sometimes I may want to read data off of HDFS, for example, some post-processing, like our buddy mentioned over there, and you know I want to take some MR job output. So you know that Mr. Job is a Python script, right? So I submit that job. Let me go back. So I submit this job with this thing down here. Nothing's stopping me from writing more code down here. So one thing that I may do is I may run this MapReduce job, and then at the bottom I'll use something like Snakebite to go pull the output data out, and then go run like linear regression or something over there. Okay? And you can use Snakebite, and I'll show you how to do that. So you just do like, Snakebite is in pip, so you can just do like pip install Snakebite, or you can compile it yourself. You create a client. This is the IP address of what's called the name node, which is the registry portion of HDFS, the port that HDFS is running on, whether or not you want to be using trash. Usually I set that as false. And then I can do like ls, I can cat, I can do all kinds of data things. The one thing that's really, really missing from Snakebite is it cannot write data. So it can read, it can do two major things. It can do metadata operations, which are like moving files or renaming files or deleting files. And it can't do, but you can't write data. But popen and a shell can. So usually that's what I do. The next one is Snakebite also has the command line interface where you can do, in replacement of the Hadoop command suite, you can do Snakebite commands. So, so this is going to be a lot faster if you're doing any sort of serious data processing stuff, and as long as you're not writing new data. All right. Any questions on Snakebite? The Spotify guys are like super cool. They've done a lot of really interesting stuff with Hadoop and Python in general, and they've got like maybe 100 open source projects that they've created that are completely random. I'm a huge fan. I was able to meet them a while ago. So, any questions on Snakebite? Yeah.
This is a general question. How good is the support for Python for things like?
So I think it's a community question. So in my personal experience, the Mr. Job guys are like super responsive. So the mailing list is very active. You get like core authors of it responding to posts. If you have problems with Mr. Job, they'll take care of it on the mailing list. I can't vouch for Hadoop. I've never interacted with their community. Snakebite is a little bit quieter of a community. Like if you had a major problem with Snakebite, I don't know if you'd be able to get the problem solved. I know the guys that wrote it, so I would just email them. But so I think it's an open source community question, right? Pig also has a very good community. Also, Pig and Hadoop in general, maybe not necessarily Mr. Job, Hadoop and Pig, Stack Overflow is a good place for those guys. Yeah. All right. Next one is HBase. So I'm not going to spend too much time talking about HBase, but HBase gives you like random read access, write access, can update data. It's based on big table. It's really important if you ever actually get serious. And a couple people have tried to implement. So the way it usually works is you create a Java object that connects to it, and then you can use this API to communicate with it through Java. HBase has this thing called the thrift gateway, which basically stands up this separate process which accepts thrift commands, which you can write Python bindings to their thrift stuff. And then it translates that on the back end to commands to HBase. And the reason why the thrift gateway needs to exist is because a typical call to HBase, you look up where data is, and then you go to the data. Okay? So there's like multiple steps of thrift, right? So there's like, you need to contact the one guy, and then I contact this guy, and then when I do more complicated things like compactions and things, the API is massive, and who I communicate with is an important piece of the protocol. So they implement this gateway thing, which eliminates that need. Now, the downside of the gateway is now everything's going through a gateway. Everything's slow. So, so both Starbase and HappyBase are these things that wrap the thrift bindings to the gateway, which then allows you to do this very nice Python writing to HBase, and reading from HBase, which is great. But at the end of the day, the performance with these guys in comparison to the Java counterpart is like, it's ridiculous. The other thing too is that both of these have had like a last commit about 6 months ago. So I would say like on my meter, they're both dead projects. So kind of a shame, but I hope somebody actually like takes the time to write real Python bindings to HBase one day. But yeah, hope for the best. Any questions on HBase? Alright. So the next one is Spark. So I noticed on the upcoming Hadoop conferences, probably over half the talks are on Spark, which is kind of funny. It's like going to a Red Hat Linux conference and all the talks being on like Postgres or something like that. But Spark was built out of this Berkeley lab that was doing a bunch of cool stuff. And Spark in general is a lot faster, does more interesting things in memory. It also has this very nice like high-level stall API, which is pretty sweet. So you're not writing things in terms of MapReduce anymore. You're like grouping things or filtering things. Like it almost looks like Pig, actually. And you know it's all very good. And also too, they have Python bindings, which I'll talk to you about in a second. These Berkeley guys also had a bunch of things that were built on top of it. One was MLlib, which is a machine learning library, GraphX, which is for graph processing, and Spark Streaming, which is streaming analytics. And then you've got PySpark, is the Python bindings for this thing. So again, Spark is a replacement for MapReduce. So you'd use one or the other. There's actually, it's a really touchy subject on like when you should use one or the other. Yeah, I'm not going to try to get into that argument right now. So some people will say Spark is like better in every single way. You should never use MapReduce again. Some people are like, well, there's some cases where that's not true, and like so. But Spark's getting better. So there's like, I would say like Spark is very exciting technology. You should definitely try it. And if it works for you, then that's good. So Spark has Python bindings, which is great, and they're native, which is awesome, right? Like I'm a super big fan of this. The major problem is the Python API is almost treated as, in my opinion, a second-class citizen in the Spark world. So the Scala bindings are fully featured and have all the new up-to-date great stuff whenever they do updates. The Python bindings are always like, seem like a step behind. Like, they get updated less frequently. So there may be some specific corner case or something like that where Python won't work for you, but it seems like they're pretty reasonable. And also, too, performance-wise, you're not taking a big hit because it is native, which is pretty cool. So, a little bit of these last two bullet points should be on the last slide. The way Spark works is, so sorry for doing this out of order. The way Spark works is that it loads data into these things called resilient distributed data sets. And what this is a data set that gets loaded into memory. Okay? And it's resilient and distributed. So that means it's distributed over lots of nodes and memory shared across lots of nodes. If one node goes down, the RDD knows how to regenerate the missing piece. So, and the way Spark will work is you do transformation over this blob of memory. So I have this memory, and I say, I want to filter out all this stuff. I want to group by state. I want to sum on integers. I want to do X, Y, Z. It's doing the transformation in memory. MapReduce is dumping the disk almost every single step of the way. So that's how Spark really gets its performance boost. And since it's resilient, they implemented this resilient way. You don't have the same problems of like, well, with typical in-memory systems where if a node goes down, it's volatile and you can't fix it. So Spark is pretty cool. So it uses memory for the most part, but if your data set ever gets too large, it knows how to like start writing onto disk so your thing doesn't just fail. So here's an example of PySpark. There's some boilerplate in here for, this was just copied off the website for system ARC processing stuff. But the meat is this counts thing. So lines, what lines is doing is it's loading a text file into an RDD, and then you have this like, I'm passing it a flat map, and then I pass in lambdas all over the place. I hope you're going to get really comfortable with lambdas after writing some Spark. So flat map means for every line I'm splitting on white space, and then map means for every token do something. And so what this map is doing is for every token, I'm wrapping that token in a tuple with a comma 1, should be familiar from word count. And then I'm doing reduce by key, and then I'm adding this add function. So add is literally add, like plus. So, or I could have done lambda x, y, x plus y. I probably would have done that instead of importing an entire model over it. And then this runs, and it does the RDD magic, right, and then spits out the result, and then I print out the results. And this is all in Python, which is cool. Like I said, here, this script doesn't stop here. You can do post-processing or something like that if you wanted to. You can do data preparation with snakebite up here if you wanted to. So, all kinds of cool stuff. All right. So, that is all I got.
There are restrictions on the functions. Obviously, you use lambda functions, but do they have to be minors, or can you just use whatever you want?
Yeah. You can just do whatever you want. So you can, you can just write your def up at the top of the script and use it down there.
And you can bring anything you want that's sort of in the C Python, because you still have this problem. You have to distribute it to all the nodes, so you still have to like everything sort of installed everywhere.
That's a good question. I'm not sure.
I want to write some Python, make some Python stuff in there.
I really don't know. I honestly haven't gotten too deep in the Python bindings. I still kind of, whenever I've used it, I still use the Scala ones. And that's not because of choice, it's because I was working with other people. Yeah.
What are the best options for getting data from HBase?
What are the,
I'm using HBase storage in Pig, and I end up reading way more data than I need, which doesn't really take that much time.
Yeah.
But I look foolish and make fun of you.
Yeah. Pig on HBase is kind of a waste, and you should just be doing it on HDFS. Pig's HBase connector doesn't utilize any of the HBase features, right? Being able to filter down data on the server side. So your best bet right now is writing scans in Java.
Short of Java? I'm sorry.
So no, it's fine. It's fine. This is a frustration I have as well. One project that's kind of exciting is Phoenix, maybe. But Phoenix is like, it changes the nature of what you're doing with HBase. What Phoenix is a like SQL type thing that runs on data that's in HBase and writes data in HBase, and that has all kinds of cool stuff. It's really promising. It's still an early project. Let's see. You can use the HBase shell, not necessarily perform it. So,
I don't want to take too much time. basically, my main problem today, I was doing this job developer from the group from HBase storage to do filtering. And we found out we had a HBase bug. So they're working to fix it, but meanwhile now I have to use the original HBase storage so I can't filter. So I'm screwed, like now I can't get anything done. I go to the shell, it's the same problem. Like I have these PDFs and that's right from JRuby or something, and I can't manipulate them to figure out how they work. And it's
So I think you should take that frustration and try to do something about it. Because I don't have a good answer to this, and this is actually kind of embarrassing, to be honest, because